Hello, all my friends around the world. We are here. We are live. This is happening. And today, my guests are Yogita Tilikuri and Tim Sander. Please, Yogita,
Hi,
tell me how to say your name exactly.
it's Yogita. You got it right.
Yogita, just did the accent on the yaw. And Tim Sander, did I say that right?
That's right. No S at the end. So I'm proud that you got it right. Everyone makes that mistake.
Oh, it's just the S at the beginning. And
Just at the beginning.
just at the beginning. Good. Where are you right now?
I am in San Mateo, California.
And San Mateo, the Snowflake office?
That's right. Yeah, I'm in a conference room in the office right now.
Excellent. And what do you do at Snowflake?
I am a product manager at Snowflake, and I work on workload optimization features like automatic clustering and the query acceleration service.
Excellent. Query acceleration and automatic clustering. How about you, Yogita? Where are you today?
I'm in Cupertino, California, and I'm a product manager for the search and some of the pruning features here at Snowflake.
Search and pruning. So we're going to have a very interesting conversation today. I'm Felipe Hoffa, developer advocate for Snowflake. Many times I'm in San Mateo, but today I'm in Sao Paulo because I love traveling and I can do this live wherever I am. And we have friends saying hi in real time. Govin, hi Anne. We have Piotr is in Warsaw. Wow, I wish I could go to Poland. Maybe soon. But let's see what we have today because I love when people ask live questions. I hope people are very interested on how to improve the Snowflake performance with storage optimization. I have a ton of tabs open already, so let me just read the titles. Optimizing storage for performance. General available Snowflake search optimization service accelerates queries dramatically. Leverage faster, more efficient search on Snowflake. We have the getting started with search optimization quick start. The blog how Snowflake updates, accelerates point lookups and analytical queries and automatic clustering at Snowflake. That's a lot. And Yogita, you are doing this webinar on November 9th with Snowflake, how to search faster in Snowflake. But from all these topics, what would you like? What are you going to show us today, Yogita? And what would you like people to remember?
Um, Today we are showing how does search optimization and clustering work and when to use what. And if you want to learn more about the search specific use cases, you can also tune into the webinar, which is coming on November 9th.
Excellent. So tune in for the webinar on November 9th with you and learn about search optimization and automatic clustering. And Tim, what would you like people to remember from today?
So both automatic clustering and search optimization that we'll cover today are awesome optimizations that you can use to improve performance in Snowflake. And I'd love if people remember when to use each one and develop a good intuition around that.
When to use each one. And developing intuition is really good. So let's dive straight into that. What do you have for us, Tim?
Yeah, so search optimization and automatic clustering are features we'll focus on today because both of these features are optimizations that improve Snowflake performance by helping queries achieve better pruning. So before we dive into talk about these features and their best practices, we want to talk about pruning and what it is and go through a quick example there. So I'm going to jump in and share my screen. And this is actually on that same blog that Felipe had highlighted it earlier that dives into lots of awesome technical details around clustering. And this blog is actually pretty advanced, but we're just going to cover the very first section of it together. But of course, feel free, read it on your own later on if you'd like. In this example, let's imagine that we have a fictional table that has 4 micropartitions. Now, behind the scenes in Snowflake, your data is organized across micropartitions. And most of the time, you'll have way more than 4 micropartitions. Many big customers have millions or tens of millions or even more micropartitions. But for the sake of this example, let's say that you have 4 micropartitions where this data in the table on the right is organized across these 4. Now,
So this is how
hypothetically,
data is stored by Snowflake.
exactly right. This is how data is stored. It's stored across many small micropartitions. And each of these micropartitions is likely on the order of megabytes in size, like single or double digit megabytes.
Excellent.
Now, let's say you ran this query here that goes and filters where type is equal to 2 and where date is equal to November 2nd. If you were to run this query on these 4 micropartitions that had these different values spread across the 4 micropartitions, I'm going to ask you a question, Felipe. How many micropartitions do you think we need to scan to run this query?
Oh, you know what? The query is a little small, so I would appreciate the zoom, and I'm
Oh,
sure
yeah. So I'll
everyone
zoom
would.
in. I'm sure everyone else would too. So I'm going to zoom in on that query there. So query is an
Excellent.
equality filter where type is equal to 2 and where date is equal to November 2nd. And I guess I'm putting Felipe on the spot because I don't know if he knew I was going to put him on the spot like this. So, I mean, feel free, as you're following along, think about this as well. How many queries, how many partitions would we need to scan to run this query here if this was the data?
So, again, I would appreciate the zoom because.
Oh, yeah. So you can
Yes.
see, yeah, it might be a bit hard to see. You can see here we have the November 2nd data on 3 of the 4 partitions and type equal 2 on all 4 of the partitions. So this query likely, when it runs, will likely end up scanning 3 of the 4 partitions. So we would not need to scan this partition here, the partition 4, because internally, each of these micropartitions has data about the values that are stored on them. Within each micropartition, we'll maintain the range of possible values for each of the columns that is stored on each micropartition. So we would know that on micropartition 4, I mean, there's no data, right? The range is 11.3 to 11.5, right? So because 11.2 isn't there at all and is not within that range, we would be able to prune it and effectively just scan micropartitions 1 through 3.
Yeah. By the way, our friend Condal on LinkedIn got the number right. He said 3.
Nice.
But 17 seconds later, he said, actually 4. And I'm wondering. So yes, let's keep the first answer because he got it right the first. And
Very
then,
nice.
yes.
So
Okay.
I guess in this case, that's not bad, right? We pruned 1 partition, but if this was a query that you ran very frequently, you might want better pruning than that. So if we used a feature called clustering, basically what we would do, and I'm going to zoom in on this so you can see it, is we would sort data within your micropartitions by a particular value. So let's say we went and partitioned or clustered the data by date, comma type. That would mean that all the data that had the same date value, we tried to store together, and then the data with the same type value within each of those date values, we'd attempt to sort across the different micropartitions and store together. So with this cluster key, you can see that only micropartitions 5 and 6 contain the data for November 2nd. And only micropartition 5 within the data for November 2nd, only micropartition 5 has the type value 2. So I'll ask you a follow-up question. If we were to rerun that query, how many partitions would we need to scan?
I think 2.
It would actually just be 1. If we had just had the date cluster key, we would need to scan most likely micropartitions 5 and 6. But because we've added the second type column to the clustering key, within the value November 2nd, we've actually gone and sorted the type values so that all of the 2s are located together. So when our query engine goes and runs the query, it can say, oh, okay, I know that micropartition 5 only has type values 2 and date values November 2nd. So I know I need to scan that. But for these others, we know that, hey, this only has type values 3 through 4. So we know it can't possibly contain 2. So we don't need to scan it. And similar for micropartitions 7 and 8 with the date.
Because Snowflake can see that range in the metadata. And I have to
Exactly
say,
right.
2 people got it right on LinkedIn. One, I cannot see their name right now, but I can see Prajakta Joshi that said just 1. So yes, two people got it right. Thank you for being interactive. 1 micropartition, way less scanning. Thank you.
Yeah. So if you can imagine, let's say you had millions of these, this could represent a really big performance improvement. So
Yes.
kind of to summarize, that's pruning. And clustering improves things by optimizing how your data is stored so you're able to prune more partitions.
Yes, and let me ask this question from Gus because he sees the value 2 on the micropartition 8, but Snowflake doesn't scan that micropartition because
it won't scan this micropartition because it knows that only dates November 4th through November 5th are on this micropartition. So because we already have an equality filter, if I go to the query on date equals November 2nd, we know that the data we need could not possibly be within this micropartition. So we don't need to scan it. And then, of course, the query gets faster as a result.
perfect.
So basically, if I were to summarize clustering in one sentence, it would be we're optimizing how your data is stored so you don't need to scan as many micropartitions. I'm going to let you get to talk a little bit about how search improves pruning, which is a little bit of a different mechanism.
Thank you,
Let's go to
Tim.
search. Hello, Yogita.
Yes. So you saw how pruning and how clustering will help reduce the number of micropartitions that are scanned. Search optimization is yet another technique which will further reduce the number of micropartitions read. This can be useful in cases where we do not have granular enough metadata, or even after clustering, let's say there is still a lot of micropartitions that need to be read, and you're not reaching your performance that you would really like for the query. So what we do in search optimization is we build an additional data structure which contains information for each and every value in that column. What are the micropartitions that definitely don't contain that value? So for example, let's say your query is select star from a table where you're finding all information with the name Martin. What we do, or what the index does, or index is a mental model for you to understand this, what it tells that for Martin, these are all the micropartitions that do not contain any data of Martin. And it will reduce the number of partitions that are read. And in this example, only one is read. So think of it as applied, let's say if clustering is present, we would cut down the data, then search optimization comes in and further cuts down the amount of data that is read, and thus improving your query performance.
So clustering knows about the range, and search optimization has an index of the actual values inside the partition.
Correct. And if you can think like the main use cases where this would be really useful is you're randomly accessing different parts of your data, and you cannot really organize by this key for most of your queries. So in these cases where you're doing point lookups and getting randomly accessing different parts of your data, or needle in haystack kind of queries, search optimization is your friend.
Excellent.
So one
Go
thing
ahead.
that you might be wondering is when should you use each one, right? Because these are both optimizations that improve pruning, but they both improve it through different ways. So it's really important to understand, I mean, when each of these features is better to use. I will say though, in some cases, it could be a situation where both of them could be great solutions to the problem. So if you're struggling with which one to pick, it's possible that maybe they're both reasonable. But in a general sense, I think of clustering as a broad optimization that optimizes lots of different queries beyond just equality filters. The mental model I'd have is clustering is changing how your data is stored in Snowflake. So if you keep that mental model, you can develop a little bit of a good intuition for the types of queries that could be improved by clustering. So for example, range filters, right, greater than or less than, can often see pruning improvements due to clustering, as well as order by, occasionally also group by, aggregations, and then joins can often see performance improvements due to clustering. But of course, the limitations are you can only pick one clustering key. So, I mean, you're restricted to one, and it's in some instances might not give you as extreme of pruning as search.
Yes, so
Yeah.
one is a physical sorting of the data, that's clustering, and you can choose one way to sort the data, while search optimization can optimize many dimensions at the same time.
That is absolutely correct. So while you're clustering by one key, but there are several queries where you have more filters. Let's say you're accessing IP addresses or user IDs. In all of these cases, you could enable these columns for search optimization to improve the query performance. So like how Tim said, like for clustering, like ordering is the queue. For search optimization, needle in haystack queries or like point lookup queries is your queue. So if you're doing a lot of these needle in haystack kind of queries on some particular filters, enabling them for search optimization would really work well. Also, another thing is the difference in the types of searches. Like in search optimization, we accelerate searches in semi-structured data, your geographical searches, and also, of course, in some structured data. But we do not accelerate your inequality queries. So whenever there is a not equality sign, that won't be accelerated by search optimization, but that would be supported by clustering. So the type of search you're doing can also guide you in which of these two performance optimization method you use.
And I think this is really best understood through an example. So we prepared one for you that's actually kind of loosely based on a real world customer example, right? And the types of challenges that customers face with these features. So I'm going to hand it over to Yugitha now, who will share her screen and begin to walk us through that.
People love examples, and I have Yogita's
And we'll talk
here.
through together.
Okay, that's awesome. Let me switch my screen.
We have a simple use case there.
Yeah. Can you see my screen? Okay.
Perfect. I can see it. A sample use case.
So we picked a use case from the cybersecurity industry. Here, this customer has their logs stored in AWS CloudTrail. So the interesting thing about this logs is that the structure of some of these fields, for example, here, the request parameters that we have highlighted, vary subtly based on the type of event. For example, the events, when the event name is start instances, the request parameters looks different than when the event name is run instances. But the use case could be that you need to perform searches where you're trying to find all logs that are relevant to a certain instance ID. Say, for example, this was a blocked instance ID and you want to make sure there were no logs that was generated by this instance ID. And this is how the query would look like in Snowflake, where you would have a filter for the range of time that you would want to do the search in, and do a substring kind of a search where you're searching for the specific instance ID in your request parameters column. So Tim, maybe you could walk through how we can optimize this via clustering.
Yeah, so for clustering, again, it's something that is likely to optimize lots of different queries that use a common column, either in the where clause or joins, or perhaps even order by our aggregations. So in this case, the time is a really good candidate because it's used as a filter in this query. So if we go and cluster the data by time, we can go and improve pruning that way. Additionally, for this particular workload, the data naturally lands in Snowflake in such a way that's already kind of sorted by time. Like for instance, it ingests data kind of sequentially, right? So we ingest data for October 25th before we ingest data for events on October 26th, and that's before the 27th and so on. And this sort of natural clustering, as we call it, can end up helping the automatic clustering service costs be a lot lower because it actually has to do a lot less work since the data is already landing in Snowflake decently well clustered. So in this case, we pick a cluster key based on time in order to go and optimize pruning. And we'll opt for hour in this case.
Yeah, that's what I wanted to note. You are not choosing the complete timestamp, but you are just clustering by which hour things happen. Why that reduction in granularity, or the opposite of reduction?
Yeah, that's a great question. So I guess hypothetically, if we went on one extreme and we clustered by the year, that wouldn't give us very good pruning, right? Because I mean, let's say this software was in production for 3 years, right? Then I guess at best, right, we'd get, I don't know, 33% pruning roughly, right? Or 33% of the files we need to scan, right? Something like that. So because the cardinality of that property is so low and there's not very many values at that extreme, it wouldn't be a great choice. On the other extreme, let's say we went and we used the millisecond or the nanosecond. In this case, we might get pretty good pruning, but because there's so many possible values for nanosecond or millisecond, it will make automatic clustering more expensive to run because it will be more work to sort the values by a higher cardinality column. So in this case, hour is kind of like the happy medium. And most of the time, for most workloads that cluster on time, customers will usually pick either the hour or the date. And this is generally a pretty happy balance between cost and performance.
Basically, you're telling Snowflake, if you see one record after the other and they are both in the same hour, don't bother sorting them,
Yeah, don't
reordering them.
bother.
Just let them be. Excellent.
And that makes clustering much cheaper, sometimes by a pretty big order of magnitude. So no reason to do that extra work.
Perfect.
Cool. I'm thinking
So
maybe we can jump to talk about cost. What do you think?
Yeah, I have one small question since we're talking about time series, and we have a question on YouTube from Mohan that says, because Snowflake, if let's say you were doing inserts and inserting one row at a time with this timestamp, would Snowflake create one micropartition for each row you're inserting, or how does it manage to have multiple rows in one partition if you are just inserting them one by one?
Yeah, no, that's a really great question. A lot of the operations that you run in Snowflake, like inserts or other DML operations, when you run these, will naturally make sure that you don't end up with a crazy number of micropartitions. So let's say in the extreme case, you ran inserts where there was one row per insert. Within the insert operation, we would, in some of the execution time, we would go and make sure that it lands in Snowflake in such a way that's optimized for query performance, which would likely be micropartitions on the order of like a few megabytes or more in size.
Yes. So if you add one row, it would choose an existing micropartition that it's mutable, but it would choose the existing one and rewrite it as a new micropartition with the same data as the previous one, plus the row.
Bingo. That's exactly right.
Uh-huh. And then clustering, what we are setting up here, would reorder them at an eventual time when it sees that there is a big mess of the timestamps, if there was one.
Exactly. And this is done asynchronously, right? So if you go and you ingest data and you get certain performance, if you go and enable clustering, it won't change the performance around your data ingestion at all. Like it wouldn't make it slower or anything like that. A lot of databases, right, when you think of an index, it's built at the same time your data is ingested. Clustering and also search optimization are entirely in the background after the data is ingested.
Perfect, because that was the
yeah,
question from Kamala Kanlan, who was asking exactly that. Will the clustering impact the transactions? No, because we insert each row wherever it goes, fast, hopefully in one of the same micropartitions that exist, and then clustering takes care in offline of resorting stuff.
Exactly right.
Uh-huh.
And then in this example here, like
yeah.
let's say we added on clustering, but we didn't get good enough pruning. Yogita, is there anything you want to share on how we could improve
Yes.
pruning further?
Yeah. So let's say you added clustering and still you've not met your SLAs, performance SLAs. What you could do here is also enable the request parameters field, which is variant in Snowflake, enable it for substring method. So this, what we do is we have a maintenance task, an initial build task, which will create something of as like an index, and you can find this instance ID that you're looking for. If it occurs infrequently in your data, you'll see that these queries are much faster with search optimization. And note that this request parameters, you can either enable the whole variant for your search optimization, or if you knew that there is a certain part of this variant that you would be searching more often, you can enable only that subsection for search optimization. This will help reduce the cost also, because you're just trying to index a part of your data rather than the whole variant.
Uh-huh. So we have two uses here. The event time gets benefits because you cluster the data, so we only go to those micropartitions, and then the search optimization is able to find that optimize for that like, which is not doesn't even show the start of the string, which clustering would do. You are just searching for that substring anywhere in the request
in the
parameters.
Yes, exactly. So now with clustering, you already boil down to, let's say, several, still hundreds of or thousands of partitions. This will point out to those 2 or 3 partitions which have the data.
Beautiful.
Yeah.
Um,
I think we can move on to the costs. Like, so Tim, if you want to
yes.
like talk about quickly about the tilt cost, then I can also show how the syntax looks.
Yes,
Yeah,
because let me tell you, we have like 4 minutes to talk about the cost, and maybe we can extend a little to do a quick round to also answer all the questions that our friends are asking. But costs are super important, so let's talk about that.
that sounds great. So I'm thinking to talk about cost and give a quick kind of summary of that. I'm thinking maybe Yugitha, you can share the demo of the search cost estimation function, and then together walk through like the output and how to think about that.
Yeah.
So I'll let
Uh,
you run that, and then we
okay,
can
sounds
talk
good.
through it together. So in
That
general,
sounds. Go ahead, Tim.
no, I can talk a bit about it while you get it ready, since we're mixing up the plan a little bit and it's live TV. So
Yes.
in general, there's 2 components of your cost for these features. There's the initial cost to build the search indexes, and then there is the ongoing maintenance cost to maintain the search indexes. And likewise for clustering, there's the initial cost to go and recluster the data, right, based on your cluster key. And then there's the ongoing maintenance cost for once your data is reclustered, we want to keep it clustered over time. And for search optimization, we have this awesome function that Yugitha is just running right now for example table, that for a given table and a potential index goes and estimates and breaks down what are those one-time costs, right, for building the index, and then what is the ongoing cost for once you built this index going and maintaining it.
I
And then
love
it's actually
estimates.
perfect timing that it just
Yeah.
finished.
Okay, Yogita, can you help us and zoom a little on that?
Okay.
Either make the window smaller or use the Chrome zoom function.
Is this any better?
Excellent, that's getting much better. Thank you.
Okay, perfect. So this is the cost estimation function that Tim was talking about. This helps estimate the search optimization costs. So it helps estimate both or 3 types of cost. The storage cost, because for search optimization, there's an additional index that is built. So there is storage costs associated with that. The initial build cost for building that initial index, and the maintenance cost, like as and when new data comes into this column or data gets deleted, we need to update and maintain this index. So there's those 3 costs that come into play. What This is the table that on which you would like to know the costs, and this is the column. Equality of label means like, I want to perform any kinds of searches on this label column and say label equal to Snowflake. And then you want to improve these searches. So you're enabling this label column for the equality indexing. And
And
this
this
is
is an
how
estimate. Oh, that's
exactly,
beautiful.
that's a good point. It's an estimate. And this estimation is based on how your workload in the last 7 days, based on the DMLs that happened the last 7 days. We are estimating what could be your maintenance cost, and based on what data already exists, we estimate the initial build costs. So in this example, this is a very static table, has not been updated in a very long time, but the build cost is just 0.22 credits. And it says that it's estimated via the sampling methodology, where we're taking a few rows and we're estimating what the cost is going to look like. The storage cost is for about 2 GB of data. And the maintenance cost is 0 here because this table has not been updated in a long time, but it says that this is 0. We show that per month. And it also shows that it's estimated based on the last 7 days of DMLs.
That's beautiful. So people know the cost, and then they can decide if they want to add this index. That maybe will make their queries way faster if they're searching for that equality.
Exactly.
And
Oh,
I'm
that's
happy to
beautiful.
share that we're working on a function just like this with a super similar structure for automatic clustering. So in the future, you'll be able to do a similar sort of analysis for clustering, as well as compare the cost between clustering and search.
I love that. We're kind of on time, but I want to ask you the last questions from the stream because the people have been very active today. Uh, but anything that you would, before I go to the questions, anything that you would love to add that we didn't get into? And I promise, if you come back, what would you like to talk about? Because I would love to have you back.
Well, there's lots of interesting stuff that we could dive deeper to with clustering, or we could also even talk about other workload optimization features. But in general, I just remember that all of these optimization features could be really cost-effective ways to improve performance and are really great alternatives to when you need to improve performance, great alternatives to just bumping up the warehouse size.
Excellent. What about you, Yogita? What do you want to?
Um, I think we just touched the surface area of what are the different types of searches we can improve. So
Yeah.
if I were coming back, like I would we can talk about substring searches, like talk about geo searches, and how do you expedite each of these different kinds of searches, and what is coming up new in this
Excellent.
area.
Yeah, it's amazing that we covered two different topics. We showed how they relate to each other, but there's so much to get deeper into. But now some questions. Fred on YouTube, this is a cool one because they use CTS, they order by a column, and the second time they order by 4 columns, and somehow ordering by 4 columns went gave them 14,000 partitions instead of 22,000 partitions. Why is storage more optimized when you order by more columns? This has to do a little bit with clustering too.
So I'm going to make an assumption on this question that Fred is asking, why would pruning be better if you included more columns in your clustering key, right? Which will change how the data is sorted. And in general, if you add more columns to your clustering key and these are used in your queries, we would expect more pruning and superior pruning in your queries. And this would, of course, lead to better query performance. The trade-off, of course, is that this would be more expensive and more complex for clustering to maintain. So the trade-off would be higher clustering costs.
Yeah. And I would say storage may get optimized if every record in a micropartition looks the same, because you can be like, oh, this whole column is the number 4. I don't need to save it a million times if you're doing a columnar format.
It's possible that when you enable automatic clustering, you might notice some small changes in storage amount, but it shouldn't be any crazy decreases or anything like that. It's you might see something like you're saying, Felipe, but the main big impact will be on query performance via better pruning.
Excellent. And now I have a question from Raja that also this one makes a lot of sense that people want to know. Is there a way we can check how many micropartitions a table has? And what's the range associated with that?
I can start with answering this one. Like even the query profile does show the number of micropartitions, like the plan on the right. If you do a select star, for example, there is one way of seeing, or when you do even with filtering, it shows the number of partitions you started with and then how it decreases over time. That's one way of seeing using the query profile.
Excellent. So you can see that you do a small select and you see it scanned 3 of 2,000 partitions. You know that you have 2,000 partitions.
Yep.
And there's also a way to measure how well the table is clustered.
That's right. Yeah. So that's the kind of
Mm-hmm.
That's the other angle where you could approach this. There's a function called system clustering information where for a given cluster key, whether it's your existing key or a new potential key, you can see how well your micropartitions are clustered for that potential key. And I think that'll really, to your question, Raja, that'll give you most of that context you're looking for around, hey, how well clustered is my data given this new key?
Yeah, that would be a great live stream to just focus on how to read the results of that function.
For sure.
And I have a question from Govin that I think mixes both clustering and search, because he's asking how partition works in like function where partial data is given to search. So we have the two things mixed in one question, please.
Yeah. So how the like function or it works with both search I can talk with respect to how it works with search optimization. So when you enable a column when you're going to be doing these kind of substring searches for search optimization, what we do is we essentially build these n-gram indexes. So let's say we have Felipe, we'll break these into 5 to 8 character long substrings and index all of these prefixes. And now whenever you're searching for any of these prefixes, we know where to find the data more easily, or partitions which don't contain these prefixes. And that's how we accelerate these searches using search optimization.
Excellent. Now I have a business question where they have logs on S3 and they can scan them using some tools. They mention a specific one, but regardless of the specific one, what's the benefit of moving these logs to Snowflake and having them doing that scanning here with these optimizations?
It all comes down to performance, right? Snowflake, you can get really good query performance. So if you need to access these logs at a large scale in a, fairly latency sensitive way, right? You need really good query performance, scalable query performance. These are, good indications that using Snowflake and using optimizations like clustering and search are really good fits for the workload.
Yeah. I would like to add to this question and the angle of security, because if I have these logs and I don't want everyone that searches them seeing everything, I could use data masking, row level security, so many policies. How do those policies interact with clustering and search?
There shouldn't be a huge consideration there, I would say, at least for clustering. Anything that you can think of, Yuga?
Yeah, so search optimization works with like row masking and column masking. So if your fields are enabled for these and you're using search optimization, both of these will work well.
Cool. So you can define your indexes for search optimization, and then if I search with a different role, it would respect that too.
It would respect that, yeah.
That's beautiful. And I have some, so Kondal is talking about system clustering depth. That I would love to go deep into, like, just a session of talking about this. I have a question from Anil that's a little longer, so we might need to save it for another one. Okay, let's finish with this one that says, is there a way for a query to run parallel threads? It's a question about parallelization. What do we think about that?
So the short answer to this is yes, right? When you run a query, there's a high amount of execution that will occur in parallel. So to answer the question directly, answer is yes. And this occurs automatically behind the scenes when you run a query. We have tons of engineering teams at Snowflake that are very well staffed to make sure when you hit run on a query that we execute it in a really optimal way for cost and performance behind the scenes. However, there is one awesome, fairly new feature that we work on called the Query Acceleration Service that is an optional feature that you can opt into as a customer that will go and for queries that have large scans that are very parallelizable, we will actually go and allocate extra temporary capacity so you can improve the performance of those queries specifically. And then when the query execution is done and we don't need that capacity anymore, we just spin it down immediately. So you really only pay when it's directly helping you.
Excellent. And with that, I want to finish with a nice comment from Michael Franco that found this stream really informative. So I'm super happy when we when we share in-depth content and we can keep going deeper. Any last words, Yogita?
No, it was really great talking with you. And this is my first live session. It was fun.
Fun. You have another session coming live as a webinar, so people have to register for that. We are going to share the link with everyone on the chat, how to search faster in Snowflake, where you will be featured with Kelly Huang, my teammate in product marketing. Last words, Tim?
No, it was awesome to be here and talk about these two great features, and excited to be on the show in the future and talk about others like Query Acceleration Service and maybe even a deep dive into clustering system information, which I think we could probably fill a whole whole call based on that one function for sure.
I would love to have both of you back. Thank you everyone for coming, And now it's my time to play the dancing bear. And stay tuned because next week we have the Halloween episode of this live. Thank you.
Bye.